In this paper, we propose the LEMMA dataset to address the goal-oriented, multi-agent collaboration activities that are largely missing in current video benchmarks. As the most readily available learning source, daily human activities vary in a large range of categories, from outdoor sports to indoor cleaning. These videos could be used to study problems like robot imitation learning, task planning, human-robot teaming, and etc. Among all the things provided, daily activities offer unique viewpoints on people's motivations and goals. For example, such goal-oriented behaviors are discussed in the breakfast dataset published in 2014. Next, the multitasking nature of humans add complexity to activity understanding. This is discussed in the multi-thumos dataset published in 2018. Finally, collaboration and social interaction of multi-agents require the ability to conduct task assignment and understand social norms. These are all important capabilities of us humans and therefore desired to be learned by intelligent agents. Previous works on video benchmarks tackled the activity understanding problem from different perspectives. For example, some of the works took a more specific view on atomic action understanding. Some used activities performed from scripts for understanding spatial temporal patterns. Many others paid more attention on the single task execution scenario, and a lot of them focused on single agent egocentric video understanding. While all datasets focused on some of the key factors mentioned previously, most of them missed certain aspects of the whole picture. Therefore, we propose the LEMMA dataset to aggregate all these features. More specifically, we design activities and different scenarios to address the understanding of goal-oriented activities, multitasking, and multi-agent collaborations. To mitigate the occlusion problems commonly found in video datasets, we provide multi-view recordings in both third-person views and egocentric views. As previously mentioned, we designed 4 special scenarios, namely the single-agent single-task scenario, where one participant is instructed to perform one goal-oriented task efficiently, the single-agent multitask scenario, where one participant is instructed to perform 2 tasks simultaneously, the multi-agent single-task scenario, where 2 participants are instructed to perform one task with one leading and the other helping, and finally, the multi-agent multitask scenario, where 2 participants are instructed to perform 2 tasks in parallel. To avoid unnatural acting from following predefined scripts, we only provide basic requirements of the task without step-by-step instructions. In the multi-agent scenarios, only nonverbal communication between the participants is allowed. We also add special instructions for leaders and helpers in the multi-agent single-task scenario to specify their roles. For example, in the instruction shown below, we instruct the leader that the helper will not know anything about the task he or she is working on. Similarly, for the helper, we instruct them to infer what the task is and offer help. We record the data in 7 different Airbnb houses, with in total 14 unique kitchens and living rooms. 2 Etherconnect sensors are set as primary and secondary third-person view cameras. 8 participants were instructed to wear head-mounted GoPros to record egocentric view videos. We annotate the spatial location of humans on the primary third-person view recordings. We also annotate the temporal location of actions on all synced recordings from third-person view and egocentric view. Human interactions with objects are highly purposive. From the simplest verb of put, we can generate various combinations of objects and target places, such as put cup onto table, put fork into drawer. Situations could become even more challenging when objects are used as tools. For example, put meat into pan using fork. So instead of using the traditional verb plus noun pattern to denote atomic actions, we design atomic actions to be compositional templates with blanks. Each blank corresponds to a special semantic position, including target objects of this action, location information, and also tool information for conducting this action. Here, we show some example templates. We use VATIC to annotate the human bounding boxes on the primary third-person view recordings. We use a self-developed annotation tool to annotate compositional action for each agent. Additionally, we annotate the governing task that each action contributes to. We believe such annotations will be helpful for the understanding of task scheduling and task assignment. Here, we show some annotated examples. As a comparison, the proposed LEMMA dataset aggregates all key factors of human activities that previous works failed to capture. And in the meanwhile, it stays at a comparable size with current large-scale video datasets. With natural interactions, we have a long-tail distribution for objects being interacted and actions being conducted. We show the co-occurrence relationship here to better visualize the statistics of the dataset. We provide baselines for two challenging benchmarks, compositional action recognition and action task anticipation. In the compositional action recognition task, we treat the action recognition problem as a multi-label classification problem. Models' performance on detecting action verbs, objects in each semantic position, as well as the combined compositional action recognition are evaluated separately in terms of precision, recall, and F1 score. We show an example evaluation in the right figure. Here, we show the experimental results of our baseline models on the compositional action recognition task. We conduct experiment on input recordings from two different view angles. In the third-person view experiment, we provide ground truth human bounding boxes for feature extraction. In the action and task anticipation challenge, given all previous observations, at each time frame, models are required to predict the next non-empty compositional action and the governing task that the action contributes to. Performance of models are evaluated in precision, recall, and F1 score, similar to the compositional action recognition setup. In this challenge, we also design a special train task split for different scenarios. In the single-agent, single-task scenario, for example, 3/4 of the videos are put into the training set and the remaining to the testing set. For the other scenarios, the train-task ratios are listed below. This follows from the intuition that, with sufficient clean demonstrations of single-task executions, interpreting tasks in more complex settings should be easier, thus requiring less learning samples. We believe such a design will encourage the model's capability to generalize. Here, we show the results of our baseline models. This dataset also provides sources for new challenges, including spatial action localization, multi-view mapping, video summarization, 3D scene understanding, and etc. We hope that such designs will boost the study of human activity understanding in the computer vision community. For more information, please check out our paper as well as our website. Thank you.